Hi, welcome to Spring Forces, section 2-8. Now, when we talk about springs, we're talking about a system that has a restoring force. Springs are very important in mechanics, oscillations, and engineering applications. Spring behavior is based on Hooke's law, which was formulated by Robert Hooke in 1678. And later on in this course, we're going to talk about simple harmonic motion and energy storage, and springs are going to be helpful on that. All right. Now, Hooke's law states that the force applied by a spring to an object is directly proportional to the distance the spring is stretched and or compressed. So F equals negative kx. Now, here we have a negative sign. This negative sign tells us that the force that the spring exerts on an object will be in the opposite direction to the displacement. Meaning that if you stretch a spring to the right, then the restoring force would be towards the left. If you compress a spring towards the left, the restoring force would be towards the right. Basically, the spring will want to return to its original or equilibrium position. Now, the K value represents the spring constant, also known as the stiffness constant. And this spring depends on the material the spring is made of, the size, the number of coils, etc. Okay? X is the displacement from equilibrium. And this Hooke's law, it's only valid for a spring within the elastic limit of the spring. If you overstretch a spring, then Hooke's law will not apply. Okay? Now, if we graph this force, if we make a force versus displacement graph, then since force is directly proportional to displacement, the graph is going to be a straight line. And the slope of that graph will give us a value of k. And later on, we're going to learn that the area under the curve would be equal to the work done or the change in elastic energy for a spring. Okay. So the spring constant has units of Newton per meter. The way to find the spring constant experimentally would be to graph a force versus displacement graph and then find the slope of that line. The spring constant tells us how easy or how difficult it is to stretch a spring, which means that the larger the K, the larger the constant, the more difficult it is to stretch or compress the spring. And as I mentioned before, the spring constant depends on the material, the geometry, the number of coils, etc. So when working with springs, we can have a system of one spring or a system of multiple springs. Okay? For a system of one spring, then we're going to have that the force applied by the spring to the object is equal to k times the displacement. And based on Newton's third law, the force that the object applies on the spring has the same magnitude but in opposite direction. Now, sometimes we can arrange springs in different configurations. Right? We can arrange the springs in series, which would be something like this, having one spring connected to the next. Now, if we want to analyze these springs, then we have to find the force being applied to each spring. So on the bottom spring, spring 2, we're going to have the total force, which is the weight of that object, and the spring is going to apply an equal force in the opposite direction, F2. And then if we look at spring 1 is going to feel a downward force, F2, so it's going to apply an upward force on the second spring. Now, based on this, we can see that when the system is in equilibrium, F total is equal to F2, which means that F2 is equal to F1, which means that F total is equal to F1, which is equal to F2. This tells me that F total would be equal to an equivalent K for the system of spring times the total displacement of the springs. And if we analyze each spring individually, then F1 would be equal to K1 times X1, and F2 will be equal to K2 times X2. Now, the total displacement that the system will stretch will be equal to X1 plus X2. So if I solve for displacement in each of these three equations, I would get something like this, where the total displacement is equal to X1 plus X2. So my total displacement is X1 plus X2. Substituting the values for each, I get something like this. And since I know that the forces are equal, I can simplify that and end up with 1 over equivalent K is going to be equal to 1 over K1 plus 1 over K2. Now, what if there were more than two springs? Then we would just continue this equation, right? All right. Another way of organizing springs would be in parallel, something like this. Okay. Now, in this case, it's a little bit different than in series, because in this case, when we do a free body diagram, we see that the total force will be equal to F1 plus F2. However, the displacement will be the same, because the whole system stretched the same distance. Okay? So, here I can say that F1 is going to be equal to F1 plus F2 is going to be equal to the total force. F1 is going to be equal to K1 times X1, and F2 is going to be equal to K2 times X2. So if I plug these values into the equation, and I know that the distances are all the same, then I can see that the equivalent K for springs in parallel is equal to the sum of the individual K's of each spring. So, to summarize this, we have that in series, to find the equivalent K of the system, we do 1 over K plus 1 over K1 plus 1 over K2 plus 1 over K3, etc. And in parallel, we add the K's, which means that by connecting springs in series, we're actually making the spring weaker or easier to stretch. And by putting them in parallel, we're actually making them stronger, more effective. Okay? So when solving problems with springs, we have to keep in mind a few things. First, we got to keep in mind where the equilibrium position of the spring is, or systems of springs. Once we know this, then we can apply Hooke's law. Keep in mind that if we have a system of springs, we probably want to work with the equivalent K and the equivalent X. Then after that, we can do Newton's laws or free body diagrams, and later on we'll be able to use energy conservation. And then, last but not least, we got to check the direction of the restoring force. Okay. Some uses and application of springs is in shock absorbers or suspension systems. Some mountain bikes have shock absorbers on the front. They have two springs in parallel, So those cars, they have 4 springs connected in parallel. Springs are also used for overcoming earthquakes. Okay, springs are used in oscillations. Some molecular bonds can be modeled as springs. Okay, and more simpler uses: pens, trampolines, mattresses, etc. All right, so to summarize, Hooke's law is F equals negative kx, where the negative sign is because the force of the spring on an object acts in the opposite direction as the displacement. To find k graphically, we need to graph f versus x, and then the slope will give us k. When springs are connected in series or parallel, we have to find the equivalent k. Connecting springs in series will make the net system weaker, and connecting them in parallel will make them stronger. Okay, and modeling springs have many physical and real-world applications, as we talked about before. Okay. All right. Thank you for listening, and I'll see you in the next topic.